Hello everyone, this is the video lecture of section 6.3, volume by cylindrical shells method. So, in the previous section, we learned the method about how to get volume when you're given a solid. The one underlying theme of all the cases we considered in this section is that when you know the cross-sectional areas, okay, perpendicular to certain axes, all the cross-sectional areas, if you know that, then integration of these cross-sectional area function will give you the volume. So that if the solid is obtained by rotating some planar region around an axis, right, then cross-sectional area perpendicular to the rotational axis will be always some kind of endless, all right? So you can use Washer's method. Now here, we will have a completely different approach. We are not going to use cross-sectional area, something else, okay? This is called cylindrical shell method. So first, think about circular cylindrical shell. Let's say you have a thin cylindrical shell. See? So these are thin cylindrical shells. A cylindrical shell is made of two concentric cylinders. One is large, one is small, in between, the space between two concentric cylinders. So here, let's say, the radius of inner cylinder is R1, radius of the outer cylinder is R2, and the thickness of the cylindrical wall is R2 minus R1. Okay? Now, and then let's say R bar is the average value of those two radiuses. So in the middle, right? Then the volume of this shell is volume of the outer cylinder minus volume of the inner cylinder. Outer cylinder volume is pi R2 squared H. They both have the same height, common height, H. Minus inner cylinder has this R1 as a radius, so base area pi R1 squared times height. Now if you factor out pi H, this is R2 squared minus R1 squared. You can write it R2 plus R1, R2 minus R1. First of all, this is delta R, thickness of the cylindrical wall. And I can write it as 2 pi H, right? Divided by 2, multiplied by 2. Then this is average radius. So you have 2 pi R bar H delta R. So this is the formula. Okay. How do we interpret this one geometrically? 2 pi R bar H delta R. Now imagine that, so let's say delta R is very, very small, so it's a very thin cylindrical shell, just like the lateral surface of your can food, right? If you cut vertically and unwrap, unfold, try to make a flat, thin rectangular plate, all right? Now if you try to unwrap, obviously inner wall, this length is 2 pi R1 is shorter than 2 pi R1. So it's not going to be exactly flat. When you try to make it flat, there will be some wiggles here and there, right? But if delta R is very small, then R1 and R2 are pretty close, right? Like a thin can, right? So if you flatten out, this is what you're going to get. This is circumference. This is H. Circumference, you know, it's not, you know, we have to choose the average value, right? The circumference of the circle, 2 pi r bar, f, when you unwrap, this length will be 2 pi r bar, 2 pi r1 or 2 pi r2. Well, let's say some of the excess material of the outer wall will be transferred to the inner wall so that they can really flatten out. And then this will be very thin. This height is delta R. So this is a very, very thin rectangular box. It's not really, doesn't really look like a box, but yeah, it's a rectangular box with very, very short height. So you can imagine that you can transform by cutting and unfold, you can transform this cylindrical shell to this thin rectangular box. What is the volume? Length, width, height. 2 pi r bar, height, h, delta. Precisely this, right? So this is not approximation, right? It is exact value. We just proved. Okay? Now we're going to use this cylindrical shell in this figuration. So let's say you are given y equals f of x from A to B, and we're going to rotate it, this one, around the y-axis. Okay? So it's kind of some funny shape of nut, right? Bolt nut. So, in previous section, we would use, you know, y. For given y, we have to find the outer radius and inner radius. Because it is vertical line, inner radius is A, your outer radius is x coordinate of this for given y. Right? If you want to use Washer's method, you have to find out this point as something about y for given y, f inverse of y. Right? You have to solve for x. So you can find your x coordinate, which is outer radius, as a function of y, which means you have to solve for x, which means you have to find inverse function. The problem is, a lot of times it is very hard to solve for x, and often it is impossible to solve. So it will be very difficult to use, this Washer method. Now here we have different approach here. Let's say, think about this thin vertical rectangle. Think of this thing is made of thin cylindrical, bunch of cylindrical shells. All right? You can imagine this one is made of these thin cylindrical shell here. Bunch of, oops. Okay, so when you have some nuts like figure, I just make a bunch of cylindrical shells of varying radiuses. So you have like a cylindrical blade of different sizes, cut a little bit larger one, a little bit larger one. Then you have layers of cylindrical shells. So we want to consider the volume as the sum of the volume of each cylindrical shell. All right, that's our approach. So we are not using cross-sectional area. We're using volume of cylindrical shells. So just like before, this is x1, x2. So this is xi minus 1, xi. This size is delta x. B minus A over n. That will be our thickness of the shell. Now, then it's not exactly essential, a slightly different height. But when delta x is very small, the difference of this height is almost negligible, almost the same. Now, what is this ith cylindrical shell? Now, the radius. What about the radius of this shell? Yeah, xi bar, isn't it? Xi bar is xi minus 1 plus xi divided by 2. See? Inner radius is xi minus 1, isn't it? Outer radius is xi, right? That's why the difference is delta x, right? So you can consider this ith shell's radius. We can take average value of this, all right? So then the volume of the ith shell is 2 pi xi bar. Height will be, we can use the height of the middle point, all right? F of xi bar. The height is the function value here. Bar times delta x instead of delta r. So your volume will be approximated by addition of this. This is approximation. The smaller the delta x, the larger the n is, the better the approximation. Exact value will be limit, if the limit exists. Limit of Riemann's sum of, not function f, but 2 pi x f of x, right? It's a midpoint rule here. That is from a to b, 2 pi x f of x dx. So if you do this, so we don't have to solve the given equation for x, which often is a very difficult task. You can just use f of x as a height function, all right? X as a radius of shell, all right? So we are using this cylindrical shell. So let's do an example. Example 1, find the volume of the solid obtained by rotating about the y-axis, the region bounded by BDV stands for bounded, okay, bounded by the curve y equals 4x minus x cubed, the x-axis for x greater than equal to 0. So first of all, we have to draw this one. Y equals negative x squared minus 4, x plus 2, x minus 2. Alright? So the graph will be minus x cubed, so the other way around. Okay? 2, 0, negative 2. This curve with x-axis, these two areas, but the positive one. So we want to rotate that one around the y-axis. So I'm going to write for here. So this will be something like this at 2. So if you rotate it around the y-axis, this will be something like this. Okay. So always we think about one thin cylindrical shell. Now, again, if you really want to use Washer's method, then you have to consider cross-sectional area function perpendicular to the rotational axis. So given y, for given y, you have to find these x coordinates. That means for given y, you have to find x. You have to solve this equation, minus 4. You have to solve this one for x. Cubic equation. This case, if y is between here and here, for given y, you will have 3 x values, right? It's not 1, it's not even one-to-one function there. We don't know how to solve cubic function. It is known, but we usually don't learn how to actually solve cubic equation by hand, all right? And then once you solve, you have to find which one is this solution, which one is this, which is this. We don't need this, we need these two. And you have to find this x coordinate as our radius, this x coordinate is an inner radius as a function of y. So anyway, this will be very, very hard. Okay? That's why it is much better to use cylindrical shell method. So, in this case, for this, we're given x, delta x, right? This shell, we consider this shell. All right? And this is xi minus 1 and xi, right? This is function y equals 4x minus x cubed. Okay? So, we'll do what? Your vi will be 2 pi, xi bar, the middle, f of xi bar, height in the middle point. Function value at the middle point as a height. That will be a very good approximation, this ith cylindrical shell. And your true volume is the limit of summation of that one. Again, right? Delta x. Limit of Riemann sum of this function. So, from 0 to 2 pi x. What is f of x? 7. 4x minus x cubed dx. We'll just need to calculate this integral. Alright? So that is just 2 pi, parenthesis 0 to 2. 2 pi, take it out. 4x squared minus x to the 4th. Okay? 2 pi, 4x antiderivative, 4/3 x cubed from 0 to 2 minus 1 over 5x to the 5th, 0 to 2. And 2 pi, parenthesis, 8. So 32 over 3 minus 32 over 5. Okay? It's going to be 2 pi 15. 5 times 32 minus 3 times 32. So 5 minus 3, 2 times 32, 64. So 128 pi over 15. Okay? Cylinder shell. 2 pi r h delta x, delta r. Alright? Now, next example. Our next example is same as example 2 on page 452. 452. Example 2. Find the volume of the solid obtained by rotating about the y-axis the region between y equals x and y equals x squared. So y equals x squared. Y equals x will intersect at 0, 0, 1, 1. Okay? That region, we're gonna rotate it around the, again, y-axis. Doesn't look this. Okay, something like this. So this region rotated. Well, this one easily can be done by using Washer's method. It's easy, it's not that hard. But let's practice. Cylindrical shell. For a given x, height. Now, the difference is radius is x. You know, let's just use x instead of xi, r. You know, this is the radius. Now, this time, for given x, the height, h, is this upper function comes from x, right? My function value, my lowest function value. Okay, so this is x and x. This is y equals x squared. So this point is x squared. So this y coordinate minus this y coordinate, x minus x squared. Upper function minus lower function will be the height, all right, of this particular cylindrical shell, right? Okay, so we are adding this one, take the limit, that means integral. X runs from 0 to 1. 2 pi radius, in this case the function of x will be x. Height, x minus x squared. Your width, delta x, becomes dx. When you take the limit, it becomes integral, right? So, your v is 2 pi from 0 to 1, x squared minus x cubed dx. Very simple integral. 1/3 of x cubed, 0 to 1, minus 1/4 x to the 4th, 0 to 1, right? So you have 2 pi, 1/4, 1/3 minus 1/4, which is 4 over 12 minus 3 over 12, 1 over 12, pi over 6. Okay? 2 pi times 1 over 12 is pi over 6. Okay? Alright, so in this case, you can do easily either Washer's method or cylindrical shell method. This one is not good for Washer's method. Only cylindrical shell method works well. Some other examples, actually Washer's method is good, but cylindrical method is not good. Okay? There are roughly three different cases. One case is Washer's method is good, but not cylindrical method. Some other group, both are equally good. Third case, cylindrical method is good, shell method is good, but Washer's method is not good. Okay? Alright. Now example 3. Our example 3 is same as example 3 on page 452. So what is it? Use cylindrical shell to find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals square root of x from 0 to 1. So, this time, this is 1, 1, 1. We rotate this one not around the y-axis, but about the x-axis. The shape will be then like this. Okay? Now, this is really easy to use washer's method. Your washer happens to be just disc, because there's no hole. In that case, we call it disc method. But disc method is the same special case of washer method when your inner radius is 0. But here specifically they ask us to use cylindrical shell method. Then this time we have to consider cylindrical shell is that piece is actually parallel to the rotating axis. Alright? So it has to be given y. So rotating this stuff over here. Okay. All right. Okay. So this time your radius r is y coordinate of this point, right? And your h is the difference of x coordinates, right? For given y is the radius. So here, y equals square root of x. But we want to write this time as a function of y. Your height is x coordinate difference. X coordinate difference. This one is actually same as x equals y squared. Right? This one is x equals negative y squared, but no, x equals y squared in any case. Okay? X equals y squared. So you can write this one as x equals y squared for given y, right? And this one, 1 given y, because this coordinate 1 here, right? Then this time the height of the shell is difference of x coordinate. Here, this was difference of y coordinate, because you're rotating around the y-axis. Rotating around the y-axis, and the shell is something about x, function of x. Rotate around the x-axis, so the shell method should be something about function of y. So your height will be difference of x coordinate, 1 minus y squared. Okay? So in that case, summation of these shells, take the limit, then volume will be, again, y runs from 0 to 1, 2 pi r equals y. H, 1 minus y squared. Delta y, the thickness of the shell becomes dy. Okay? So, this is going to be just 2 pi, 0 to 1, y minus y cubed dy. I mean, this is really easy integration, and you're going to get pilot for this. Okay? Now, the last example is What if your rotation axis is not x-axis nor y-axis, something parallel to those? That would be example 4, our last example. Page 452. Okay? So, this is the find the volume of the solid obtained by the region, obtained by rotating the region bounded by y equals x minus x squared, y equals 0, about the line x equals 2. So this is the, y equals minus x squared minus x squared plus x minus x minus 1 going through 0, 1, right? We're going to rotate this one, 0 to 1. So this is y equals x minus x squared. And y equals 0. This region will be rotated around x equals 2. Alright? Then you're going to have this over here. 2, 3, and 4. Again, you want to consider cylindrical shell. This is better with cylindrical shell. So given x, your cylindrical shell, what is the radius? Your radius is x coordinate difference. 2 minus x is the radius. Not x minus 2. 2 is larger. Your graph is given here, not this one. This is just the image, the other side when you rotate it. This is the given region. So the area, the radius of this particular shell corresponding to x coordinate x will be 2 minus x. What about h? Height, h. Well, difference of y coordinates. Well, this one is y equals 0. So this point is, when given x minus x squared. So h is the y coordinate as a function of x, this, right? So that will give us this. Integral x runs from 0 to 1, right? 0 to 1. 2 pi radius times height. Okay? And delta x becomes dx when you take that. So, it'll be just integral of what? Take out 2 pi, 2x minus 2x squared minus 3x squared plus x cubed. This is really easy polynomial. So, whatever that is, you're going to get pi over 2. Okay? So, cylindrical shell can be very useful. But then let me give you one advice, warning. A lot of times, a lot of students get so excited after they learn cylindrical shell. And over the years, I found that students feel more comfortable with shell method somehow, and they prefer to use cylindrical shell method over washer method when the problem is actually more suitable for cylindrical shell method. Maybe because it's the most recent one they learned, more recent than the washer's method. I don't know exactly why, but I have seen that over the years. But be warned, cylindrical shell method is not a panacea. It doesn't work all the time. It works very well for certain problems, but not so well for other problems. Sometimes completely non-effective and not working at all for other problems. So you have to have an open mind that some problems should be done by washer's method, some other problems should be done by cylindrical shell method. Okay? Alright, this is the end of section 6.3. Thank you.